From the screen in your hands to the server farms running the global internet, everything depends entirely on the continuous movement of trillions of electrons. In its natural state, electrical energy is incredibly volatile. A lightning strike illustrates the problem. Without a framework to guide it, raw electrical current is chaotic and eager to discharge into any available path. This leaves us with a problem of control. How do we harness a force that we cannot see, hold, or contain? We use the logic of mathematics to create the boundaries that physical structures cannot provide. The first attempt to tame the unruly electron began with the physicist George Ohm. He observed that at a constant temperature, the current flowing through a conductor is directly proportional to the voltage and inversely proportional to the resistance. He formalized this relationship with the equation V equals I times R. A few decades later, Gustav Kirchhoff shifted the focus to the systems level. He established rules for how energy behaves across an entire interconnected network, defining the limits of every branch and junction. This diagram illustrates Kirchhoff's current law. It states that the total amount of current entering a junction, or node, must perfectly equal the amount of current leaving it. He also defined Kirchhoff's voltage law, which dictates that in any closed electrical loop, the total energy supplied by a power source will be entirely consumed by the elements inside that loop. These laws transformed the unpredictable movement of electrons into a series of predictable mathematical models. Modern electrical grids function as massive, interconnected matrices of thousands of components and intersecting pathways. To solve for the behavior of electricity in these webs, engineers use nodal analysis. They select one point on the circuit as a zero-voltage reference, a ground, breaking the grid into simultaneous algebraic equations. By applying Kirchhoff's current law to those non-reference nodes, you determine precise voltage values across the entire network. When a system becomes too dense to track manually, engineers turn to Thevenin's theorem. Thevenin's theorem allows us to mathematically collapse a complex schematic. Even the most chaotic web can be represented as just one equivalent voltage source in series with one single resistor. The ability to simplify an overwhelming network into a single, solvable pair of components is what makes these massive systems manageable. There is a complication, however. The electricity in our homes is alternating current, or AC. The flow of electrons reverses in a constant sine wave. Mapping a wave that changes magnitude and direction through time requires rotating vectors called phasors. These allow engineers to track the AC signal across a circular, complex grid. Because of resistance and induction, the voltage wave and the current wave rarely peak at the same time. This gap, the phase difference, means that a portion of the generated power is not performing useful work. This is the power triangle. The base represents real power, which performs the actual work. The vertical side represents reactive power, energy that merely bounces back and forth inside the grid without being consumed. Managing these phasors and power factors ensures that the energy generated at the power plant actually reaches the machines it is meant to run. All of this theory exists to design the physical hardware that manipulates our reality, beginning with the transformer. A transformer operates through mutual induction. By using a laminated steel core wrapped in two separate wire coils, it transfers alternating current via a magnetic field, without the two circuits ever touching. By altering the number of windings between those two coils, the transformer acts as a regulator. It steps the voltage up for efficient long-distance travel, and then steps it down to a usable level for the end user. These devices function as the physical gatekeepers of the grid, scaling energy to fit specific technical requirements. The final destination for this energy is the motor. This is where electron flow is finally converted into mechanical force. As shown here, Fleming's left-hand rule dictates that passing an electrical current through a magnetic field generates a perpendicular physical thrust on the conductor. In a DC motor, this force is applied to a central armature. A steady current maintains this pressure, creating torque, the twisting power that makes the motor spin. The movement of electrons is now turning gears, driving conveyor belts, and powering the mechanical systems of the modern world. These principles translate the variables on a page into the tangible rotation of motors and the mechanical force of our